So now we're going to have a delightful discussion about the different measurements. We're going to do some math here, but we're going to start with unit sets. So essentially there are two fundamentally different unit systems: the imperial, which is used by the United States, and metric, which is used by the rest of the world. Science uses metric system. Within the metric system, there are sort of subsystems. So there is an international system of units, or SI. So an official units that you use in science must belong to international system. In reality, when people report science, when people do experiments, they use all kinds of combinations of metric units because it's sometimes more convenient. Sometimes it's easier to express the density in grams per cubic centimeter than in kilograms per cubic meter. Okay? So in the metric system, the key unit for volume is 1 liter. In international system, it's a cubic meter. These units, although they are different, they are all connected. Just as an example, 1,000 liters, they comprise 1 liter. Okay? Well, length matches. Again, mass. In the metric system, we use gram. In the international system, we use kilogram. Right? So this is your kilogram. How they are related? 1 kilogram contains 1,000 grams. Make sense? Temperature. Degrees Celsius versus Kelvin. I'm going to repeat certain things, sort of kind of a bureaucratic, I would say. When you talk about the temperature in Celsius, right now, for instance, outside, it's -5 degrees Celsius. You use degrees Celsius. When you use Kelvin, I can say that outside now is 268 Kelvin. 1 degree Celsius, size-wise, and 1 Kelvin are the same, but the zeros, the reference points are different. We're going to talk about them. And the time is second. Okay? But units of time are universal in the world. So we're going to start with a volume. And I have to ask you folks, on Monday you had to calculate a volume of rectangular object. Remember this little like bricks? How did you do that? Length by width by height. Okay, perfect. So volume is the space occupied by a substance. I don't need to explain what the volume is. Let's jump straight to the units. Sounds good? Because this is one of the tricky parts. This is one where but students kind of start to flunk. In international system, it's a cubic meter. So what is a cubic meter? Can anyone tell me? How would you describe the volume that is 1 cubic meter? The person has no idea what you're talking about. I'm not going to torture you. It's the volume of a cube with the sides 1 meter. Check this out. Okay, cube, more or less. sides are 1 meter. Okay, so what is the length of that cube? What is the height? What is the width? So when we multiply all of that, you get 1 meter cubed. Any questions on that? Now, kind of jumping ahead of a train a little bit, okay? I'm going to define a liter for you. It's a cube, and I'm not going to draw all 3 sides. With a side 1 decimeter. Okay? Good, everybody? So what is 1 decimeter? Exactly. Okay? So we can say that 1 meter contains 10 decimeters. Would you agree with me? Yes? So if we do this, we would have the volume of 1 decimeter cubed, but we don't use that unit. We instead use liter. Any questions on that part? All good? So a small reminder that 1 cubic meter is the product of multiplication of three like just 1 meters, right? So I can write down this, or I can write down this. I'm going to stop right there. Does that make sense? Do you agree with that sort of transition? If I go too fast, stop me. Tell me to slow down. I'll do it. AJ? Yes. Do you follow? Yeah. Perfect. I can't read your mind, minds. So we get, what is the number that we get as a result? If you 10, multiply by 10, multiply by 10. What is it? 1,000. Okay? 1,000 decimeter cubed. Everybody agrees? Yeah. But instead of decimeter cubed, yes. So I'm going to highlight some of the relationships here. This relationship. And now check this out. This relationship. 1 cubic meter contains 1,000 liters. Okay, sounds good? I'm going to torture you with one more. So if you have a tiny little cube with a side of 1 centimeter, okay? Do you agree with me? Perfect. Okay. No, it's all fine. So if you are familiar with prefixes in metric system, okay, deci as Zachary said, 1/10. Santi is 1/100th. Okay? So we can put this relationship forward. 1 meter is 10 decimeters. Everybody follows me on that? Or 100, sorry, that's too many zeros, centimeters. Just a term, like Santi 1/100th. So 100 centimeters will make a meter. Do you agree with that? Also, we can say that 1 decimeter is 10 centimeters. Good? Makes sense? So what I'm going to do the math for 1 liter first. So 1 liter is 3 times 1 decimeter multiplied, right? So I can replace them with 10 centimeters. 10 by 10 by 10 is what? 1,000 centimeter cubed. So 1 liter contains 1,000 cubic centimeters. Question? Sure? Okay, now hear me out. When we're going to get to the prefixes, santi, deci, kilo, blah, 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 all that kind of milli, all kind of stuff, okay? For instance, we mentioned that, 1 decimeter is 1/10 of a meter. Remember? So if I ask you, okay, 1 cubic decimeter, what fraction of a cubic meter is that? You think, well, it's deci, it's got to be 1/10 as well, but it's not. It is 1,000th. Am I making sense? What I'm trying to tell you, when you talk about the primary units, meters, grams, liters, and I ran out of fantasies. But anyway, when you talk about them, you can use prefixes all you want. Santi, deci, blah, blah, blah. When you start talking about volume, you have to be very, very careful. Because 1/10 of a cubic meter is not 1 cubic decimeter. Clear? We're going to get back to this when we're going to do unit conversions. Okay? Good? Okay. Let's go back to our volume conversation. We're gonna be learning establishing more useful relationships than that, but since we are working and learning in a country which uses both systems, metric and imperial, those are the relationships between 1 liter and a quart, or milliliter and a quart, okay? So 1 liter is 1.06 quarts, and 1 quart is 946 milliliters. On the related note, how familiar are you with Saturday Night Live? I mean, you know about its existence. When you have time tonight at home, please go on YouTube and Google Nate Bargatze, Washington, SNL. It's about George Washington talking to his compatriots. It is directly related to what we are about to talk, and it is hilarious. It is one of the part 2 is also great, but part 1 is super relevant to what we talk about. Okay? Length. Meters. Well, we measure length in different units because it makes sense to express the length of an object in appropriate ones. So for instance, well, we have a joke in Russia that length is applied only to dead people, not to living. But let's say if you would lay me down, my length in centimeters would be 179. Okay? Reasonable number. My length in meters would be 1.79 meters. You can express my length in millimeters, which would be 1,790. It's ridiculous, but you can. So my point is that you use units also based on the size. You can like go from millimeters to centimeters to meters to kilometers, depending on what you're talking about. In chemistry, we use centimeters for the most part. So relationships. Well, we already mentioned that 1 meter is 100 centimeters. And these are relationships between inches and yards. Okay? How many of you are thinking now, holy crap, I will have to memorize all these relationships between imperial and metric units? No. You will have a handout on the first exam, which will contain those relationships. And if it doesn't, just come over and I'll happily Google it for you. I hate when people try to memorize something that is easily Googleable. Okay? Am I making sense? You will get questions to convert from one system to another, but you will have the relationships. Okay? Mass. Quantity of material. Okay. So SI unit is kilogram. In chemistry, we rarely work with kilograms. We work with grams. So that is our unit. Kind of a 5 out of 10 question, maybe not. What is the difference between the mass and the weight? Very, very scientific. I'm asking like scientifically, what is the difference between the mass and the weight? Go on.
Isn't the weight the gravitational pull of the mass?
Yes. Like if we want to be absolutely pedantic, it's the force with which you're, like what you're standing on or what you're hanging from pulls you back, because every force has an opposite force. Okay, but yes, it's gravitational. Well, no, that's like you're standing right now on that floor. Okay, do you have a mass? Yes. Do you have weight? Yeah, because the floor reacts to your mass by stopping it from falling. Okay. Horrible situation. It's gone. Start falling down. They have mass. They have weight. Not anymore. You have seen probably the footage from like International Space Station with all the astronauts just floating around. Do they have mass? Do they have weight? No. Because, again, mass is a fundamental property of matter. Weight is the force with which different objects interact, okay? You can feel a bit of a weightlessness if it's a very fast elevator that goes down. When like everything goes up, that's you being. And you can experience weightlessness. I don't know for how much money. You can be in a plane and the plane turns off the engine and pretty much starts falling down. and you would float in a plane, just stuff like that. Okay. Relationships, 454 grams is a pound, and 1 kilogram is 2.2 pounds. Temperature, okay. So temperature scales that we're using in science are either Celsius or Kelvin. So degree Celsius and Kelvin. Remember, we don't use degree with Kelvin. Now, one of my favorite illustrations about Fahrenheit versus Celsius versus Kelvin comes with a reference point. Before we go on, Kelvin describes absolute temperature. There is no negative Kelvin. 0 Kelvin is the absolute lowest that can be in nature. Am I making sense? Now, in terms of the step, Celsius and Kelvin have the same number of steps, same number of, degrees. So basically, it's this. So if this is 0 Celsius and 100 Celsius, 273, 373 Kelvin, you can see that the distance between 2 points in both cases is 100. Okay? But the meme that I like is actually different. So at what temperature does water freeze in Fahrenheit? Okay. So 0 Fahrenheit. Is it cold? Yeah, it's pretty cold. At what temperature does water boil in Fahrenheit? 212, but 100 Fahrenheit. Is it hot? But like if you would step out, you'd be fine, right? Yeah? Huh? Yeah. So, and if you would step out in 0 Fahrenheit, well, I mean, appropriately dressed, would you be fine? More or less. Right? Cool. So, at which temperature does water freeze in Celsius? 0. And at which temperature the water boils in Celsius? 100. So, alive, obviously, 0 Celsius, dead. So, at which temperature does water freeze? We don't even care about boiling. At which temperature the water freezes in Kelvin? In Kelvin. 273, yes. 273. So what do you think about 100 Kelvin, which is negative 173 Celsius? Is it cold? Very much so. That's the fundamental difference between 3 scales. Obviously, it's a joke, but you get the gist. Time, seconds, sometimes we use minutes. Okay. So now it's fairly easy, so let's go. This is a fantastic example, which has an answer in itself. Kilograms is what? Meter. Grams. Liters. SI unit for volume, specifically SI, not liter. Meter cubed, mass, length, Kelvin. Okay? There are certain calculations in which we cannot use Celsius. We must use Kelvin. So now we're getting into this whole conversation about significant figures. So numbers can be counted and can be measured. Do you agree with me? You measured some stuff on Monday. Remember what we were talking about. That you measure so that your very last number is uncertain. Okay? Estimated digit. So when you use a ruler, when you measure length, you count number of these marks. So you certainly have all the way up to 4. That makes sense? And then you estimate what your last number is. So you say that the length of the object that you are measuring, considering what type of tool you use, is 4.5. This 0.5, are you sure that it's 0.5? Not really. So estimated, right? Now, what he did on Monday. So this is 4 of what? Units, centimeters. Then each of these little tiny marks is what? Millimeter, 1/10 of a centimeter. So you have 1, 2, 3, 4, 5. So 4.5. These are certain. Okay? And then you have that last number. That's your estimate. Does that make sense? Good? Clear? Awesome. So when you look at this measurement, you may notice that the length that we write down isn't not 3 centimeter. It's 3.0. Why? So again? It should include that last number that we estimate. So we estimate that it's not going a little above. We don't know, but we estimate. Okay? So let's figure out the length of the red line. This one? Dissenting opinions? Yes. Hear me out. Look, are we certain about 9? Are we certain about 1, 2 millimeters? We need to add an estimated number, and we think it's going to be 0. Okay, makes sense? Now we're going to talk about, you can, taking a little pause. You can expect having questions about these measurements and questions about significant figures on the exam. Okay, and it will be important. Like if you need to report something, some small calculation, by the way, have calculators with you, some small calculation with a certain number of significant figures, you may have two answers that look the same mathematically, but only one has the proper number of significant figures. All right. The rules are the rules. Significant figures are applied to measured numbers, not counted. Can you tell me why? So if I get a ruler and I measure the length of that table, am I going to add the estimated uncertain number at the end? Yeah. Well, I measured with the ruler. It's a measured number, right? So say like, oh, it's I don't know, 120 centimeters and 0.20. Okay, because I look at it. When I count people in this room, I count 9. Is there any uncertainty? No. When you count something, there is no uncertainty. Okay? This is why counted number, like 9 people, this number has unlimited number, like all significant figures. If I would count 1,100, all significant figures in the world, every digit is significant. So, basic rules for significant figures. Non-zero numbers are significant. No exceptions. Zeros depend on the position. So these 4 examples, as you can see, contain 4 numbers, and each number does not have zeros. So if you have 5 non-zero numbers, you have 5 significant figures. Make sense? If you have 2 non-zero numbers, you have 2 significant figures. Now, zeros between non-zeros. They sometimes called trapped zeros. Okay? So now look at this. This number, how many trapped zeros do you have? 2. This number, 1. Because these 2 guys, they are not trapped. They are leading. Okay? Good? So you have only 1 number. Okay? Well, actually, no, yeah. And this one has 2. Yes, this one has 2. So trailing zeros at the end. Okay? So in this number 200, we presume that there is a decimal point right there. Okay? Trailing zeros give us 4 significant figures. And leading zeros. Okay? Am I making sense? Leading zeros are not significant. So this is why in this example, we had only 1 trapped zero and only 3 significant figures. Does that make sense to everybody? Go ahead.
So, I know I'm speaking, significant figures are also put on the.
Can you repeat your question?
I'm sorry.
No, I'm processing.
So I'm trying to understand which one would be the significant figures in the trap.
Trapped 0 is one of significant figures. No, only one. This is the only trapped one. Okay? Here's what I'm gonna do right now. I'm gonna make up a number. Okay? So how many significant figures? 4. Let me show you. Leading 0, not significant. Say again? Because this is 0, not a decimal number.
One way I think about it is like for the 0 or the 0.0702, like if you wrote it in scientific notation, that first 0 after the decimal point you wouldn't include.
They gone.
7 point.
Yeah, that's actually a very good point. Thanks, Zach. So let's write this number in scientific notation, shall we? Where should I move the decimal point? After the 7. Those zeros are gone. That's it. So, leading, non-significant. Trapped, significant. Trailing, significant. Say it one more time. Yep. Clear? Of course. And thank you for stopping me and showing everybody else that I am not dangerous. I will answer your questions. Students told me before that I look intimidating. I don't know how. Okay. So another thing, and this is sort of a very fuzzy border between the two. So remember how we talked about the trailing zeros? Sorry. This one. You have to specify that those trailing zeros are actually significant. You can specify it by putting a dot here. So they're not entirely correct in that example. Because sometimes, yes, thank you. When we write this down, okay, these can serve as placeholders, just showing that this is the precision with which we measured. Or they actually serve as a significant figure, but it must be mentioned, it must be annotated. Okay? Let me explain. And Zach is right. Scientific notation answers all your questions. Okay? So in case of 44,000 kilometers, I'm asking you to write it in scientific notation. Now those 3 zeros disappeared. But what if I tell you that I was measuring that distance using gigantic 1 kilometer, like gigantic ruler, and this is my estimated uncertain number that comes from a measurement? How would scientific notation look like in this case? Say again? No. So decimal rule is the same. So you still do 4.4, but now I tell you that this is the decimal point in the original one. Like all those 3 zeros, they actually show there's nothing in there. I literally measured it. So go, okay. That's fine. It shows you how precise your measurement is. Does that make sense? Good? And it can be applied to anything here. If I had some big ass scales that can go all the way down to that individual gram, then it's not just placeholders. Okay? But to show it, I have to put a decimal point in here. To show it, I have to put a decimal point in here. If I don't, and nothing is mentioned about those trailing zeros, they're placeholders.
So on quizzes slash exams, are you going to include it as what you want to include those?
Yes. If you have a question about the number, this number, and how many significant figures does this number have? The answer is 2. If I ask you, how many significant figures this number has? 3. Okay? Good? Everyone? Fantastic. So these trailing zeros, as we mentioned before, since they are past the decimal point, and they're always significant. In scientific notation, all zeros are significant. Okay? And thanks to Zach, like this is a number that has only one significant figure because all the zeros are placeholders. If I would do this, you would know all of them suddenly became significant. All right? Makes sense? Awesome. This is an example. A period. Okay?
If you're counting, like let's say it was like 50 cell phones, and not like something that was measured, if it was just something that was a counted number, is that unlimited or infinite?
Infinite number of significant figures. We don't apply the concept of a significant figure to counted numbers. Okay? Only to measured. Okay, significant figures for A. 4, scientific notation. Yes. B. 5 significant figures, scientific notation. Multiplied by 10 in the power of 1. You write a power. C. 4 significant figures. AJ, what's up? Okay. I have a brain fart. Yes. Thank you. 4 significant figures, scientific notation. Multiplied by okay, 10 to the power of 6. I'm going to pause right here and ask if it makes sense. Okay? Now, I'm going to talk about it on the side. Significant figures and mathematical operations. Okay? So, in addition and subtraction, list number of digits after decimal point. Okay, let me show you. So let's say we have two numbers, 32.5, and we add 4.65. Which of these two numbers have less stuff after the decimal point? 32.5. So it means that the result, and I'm gonna do this. Look at this. So I'm gonna put a temporary number. If you add those two, what you're gonna get is 37, okay? 15. If you do it on a calculator, this is what calculator is gonna show you. Am I making sense? But how many numbers after the decimal point the first one has? Only one. So you have to round it up. You have to write it this way. It wasn't the greatest example, actually. I rounded it up. That makes sense? I'm gonna do one more without rounding, and it's gonna be simpler. So let's say we have 14.77 plus 4.2. When you put it in a calculator, the answer is going to be 18.97. 72. Let's put it 72. It's better. 18.92, okay? So, but the least number of digits after the decimal point is 1. So you're ditching 2. 18.9. Make sense? Multiplication and division. Least number of significant figures. Okay? So I'm trying to think about something that I can do without calculator. Okay, let's say you multiply. No, that's a shitty example. Okay, I'm gonna embarrass myself. 120, no decimal points, nothing. I'm gonna multiply by 175. Okay? How many significant figures in the first one? How many significant figures in the second one? 3. So the answer, 17,500 plus 35. I think it's gonna be 21,000. Yeah. So this is actually like, you can leave it like this, because this number 21,000, how many significant figures does it have? 2. So good. It's just with addition, subtraction, I can quickly do it, like come up with it with examples. But let's say if you do something like ridiculous, like 5.6 multiplied by 0.3478, how many significant figures should be in the answer? 2. So I have to round it up, or just draw the trail, whatever. Okay? Am I making sense? Prefixes. Right. So when we go from one unit of length to another unit of length, for instance, from meter to kilometer to millimeter, you notice that there are prefixes that have certain values. So, for instance, here, the prefix kilo means 1,000. Okay? So, 1 kilometer is 1,000 meters. 1 kilogram is 1,000 gram, and nobody uses kiloliters. So this is the table of prefixes. In reality, what we're using in like real life, in chemistry, in measurements, we use kilo, we use deci, centi, milli, micro, nano, and pico. These big-ass prefixes like mega, giga, and tera, here's what we use: giga and tera and mega for computers, megabyte, terabyte, gigabyte. And we use mega for nuclear weapons, megatons, power of explosion. So for the conversion, it is sort of a convenient thing to represent it on the line. U is unit, gram, liter, meter, whatever. Good? So then you divide that line by the fractions of 10. So it's 10, it's 100, 1,000. Does that make sense? Okay. And the greater units are on the left. Okay? I will illustrate all of it, don't worry, okay? So milli, centi, deci, micro. Okay, sounds good? How you operate this. Some of you may be familiar with this, some of you may not. So let's say I want to say that the distance between Cleveland and Columbus is 176 kilometers. Okay, good. We can say that there's a decimal point here, just a tiny little decimal point. Good. Now I want to go from kilometers to meters. So meter is the unit, right? Do you follow? Meter is the unit. This is your kilo, this is your unit. How many steps do you need to take, and in which direction to get from kilo to units? How many steps? Which direction? So we move that decimal point 3 steps to the right. Okay? And we put placeholders in here. So 176,000 meters. That make sense? Say it again. Absolutely. My point is, if I ask you to convert 35,000 micrograms into kilograms, it's a pain in the ass, dude. Okay? By the way, let's do it. So you have 35,000 micrograms. They can also be written like this. And I want to get it into kilograms, okay? Here's micro. Okay. Now, I don't want to kind of put more crap on the image. Can you count how many steps you have to take to get from micro to kilo? 9. You can literally like 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, cool. Which direction? Left. One, 2, 3, 4, 5, 6, 7, 8, 9. This is the decimal point. Put placeholders. That's your mass in kilogram. Okay, makes sense? Everybody? Fantastic. So these are some examples. We're probably not going to be using nano and pico. I doubt that. Well, it probably can be mega. To be on the safe side, learn these prefixes and learn what they mean, okay? This is just an example of different values and using different units. But let's get to the learning check, and we're going to take a break afterwards because I need to deal with the software stuff here. Okay, 1,000 meters is 1 kilometer. 1/1,000,000th of a gram. I'm going to roll back to the table, don't worry. 1/1,000,000th micro, look at this. 10 and -6, right? And 1/10th of a liter. Deciliter, yes. Okay. So let's pause.